Okay, so let's talk about the Euclidean algorithm. We've already seen definition and several theorems regarding the GCD, the greatest common divisor. But now we want to ask, how do we actually calculate the greatest common divisor? So let's say I give you two numbers and I ask you for their greatest common divisor. Okay, so let's say I give you whatever 1800 and 366. What is the greatest common divisor of these two numbers? How would you actually calculate this? So this algorithm that I'm going to present is going to be based on just one very simple theorem, and this is the theorem. Remember that we had this division algorithm. So if I had two numbers A and B, I could write A as Q times B plus R. So suppose that A and B are positive numbers for now. And let's say that A is equal to Q times B plus R, where R is between 0 and B minus. Okay. What can I say about the GCD of A and B? I claim that the GCD of A and B is the same as the GCD of B and R. GCD of B and R. Okay. So if all of these things, then GCD of AB is equal to GCD of BR. Now, why is this the case? So let's just take any number that divides both A and B. Thank you. So let's say that D divides A and D divides B. Okay. What do I know about R? R is just A minus QB. Okay. So if D divides A and D divides B, D will also divide R. Right? So what I proved here is that any number that is a common divisor of A and B is also a common divisor of A, B, and R. Okay. But now let's look at it from another point of view. Let's look at B and R. So let's say I have some other number D prime that divides B and also divides R. Okay. But what is A? A is just Q times B plus R. If D prime divides B, D prime divides Q times B. And D prime divides R, so it divides Q times B plus R. So D prime divides A. Okay. So not only GCD of A and B is the same as GCD of B and R, but I can actually say something much more powerful. I can say that any number that is a common divisor of A and B is also a divisor of R. And any number that is a common divisor of B and R is also a divisor of A. Okay? But what I need for my algorithm is just the equality of the GCDs. So whenever I have two numbers A and B, and I just do the division algorithm, I write A as QB plus R, then I know that the GCD of the two initial numbers, A and B, is equal to the GCD of B and R. Okay, so this gives me a very simple algorithm, and this is the Euclidean algorithm. So let's say I want to compute GCD of A and B. I just check, is A a multiple of B? If A is a multiple of B, then just the GCD is just B, right? So I say if B divides A, if A is a multiple of B, then return B. Otherwise, I know that the GCD of AB is the same as GCD of BR. Okay, so let Q and R be such that A is Q times B plus R, I just say return the GCD of B and R. Okay. Now, if I want to write this more in a C++ format, I would actually write something like this. I would say that I want to compute the GCD of A and B. Let me see, do we have a monospace font? I really don't like to write code in this font. Yes. Didn't change anything. Why doesn't it change the font? It doesn't change the font for some reason. Okay. I want to compute the GCD of A and B. I just say if the remainder when I divide A by B is 0, then return B. Otherwise, return the GCD of B and A modulo B. Right? So this is basically saying the same thing. So it's literally 4 lines of code. Great. Why is this algorithm correct? This algorithm is correct because of this theorem. Right? So if A is a multiple of B, of course, the GCD is going to be B. And otherwise, I'm just using this theorem that says that the GCD of A and B is GCD of B and the remainder. Okay. Why does this algorithm terminate? We have to always constantly ask ourselves, why does the algorithm terminate? So you have to, again, find some value that is decreasing in every iteration of this algorithm, in every function call. And you have to say that this is a natural number or an integer value, and it cannot decrease forever. And here, what you can do is you can look at the absolute value of A plus the absolute value of B. And that's something that is definitely decreasing. Right? Because I keep B, but I'm basically replacing A with A modulo B. And the absolute value of this number is less than the absolute value. So because this is decreasing and because it cannot be less than 0, this algorithm terminates. This is called the Euclidean algorithm. It's our way of computing the greatest common divisor. Okay. But actually, the nice thing about this algorithm is that it doesn't only give us the greatest common divisor of A and B, it even tells us how we can write the greatest common divisor as a linear combination of A and B. Right? Because what's happening here? So let's say that when I find the GCD of B and R, it also tells me how to write the GCD as a linear combination of B and R. But then I know how to write A as a linear combination of B and R. So I know how to write my GCD as a linear combination of A and B. So I can just trace the steps of this algorithm, go back and figure out how this GCD could be written as a linear combination of A and B. Okay. But enough about the Euclidean algorithm. Actually, in 3711H, you will also analyze the runtime of this algorithm. And you will see that it has logarithmic runtime. So it's a super fast algorithm. But let's just do an example. I want to find the GCD of these two numbers. Okay. So is one of them a multiple of the other one? If I divide 1800 by 366, is the remainder 0? No. Actually, I have something like this. I will have that 1800 is going to be 4 times 366 plus, let me see, 1800 minus 4 times 366, 336. Okay. So what does this tell me? It tells me that if I wanted to find the GCD of 1800 and 366, I should instead find the GCD of 366 and 336. Okay. So 366 is 1 times 336 plus 30. So now I have to find the GCD of 336 and 30. Okay, I divide again. 336 divided by 30. Yeah, it's 11, but what is the remainder? 6. Okay, so this is 11 times 30 plus 6. So at this point, I need the GCD of 30 and 6. But 30 is a multiple of 6, if I'm correct. So this is just going to be 6. So the whole GCD is 6. Okay. Great. And as you can see, this is just applying this theorem over and over again. Now we want to define something else. We want to define kind of the opposite of GCD, which is LCM. So LCM, or least common multiple, again, just like GCD, I can give you two equivalent definitions. I can say, suppose that I have two numbers A and B. So let A and B be two numbers. Again, not both of them 0, all the good things that you already know. Let's say both of them are non-zero, just because I don't like 0. Let A and B be non-zero. I define the lowest common multiple of A and B is an integer L. I don't want this to be negative, so I say it's in N, such that it has two properties. The first property is that, of course, I want it to be a common multiple of A and B. So I want to say that L is a multiple of A, and it's also a multiple of B. The second property is that I want to say it's the smallest number that has the first property. So if there is any L prime such that L prime is a multiple of both A and B, then L prime should be greater than or equal to N. Okay, so I want L to be the smallest number that is a multiple of both A and B. Now, just like the case of GCD, instead of saying that L prime is greater than or equal to L, I can write that L divides L prime. I can define it like this. And it turns out that the lowest common multiple with this definition exists. And of course, when it exists with this definition, it will also give us the one with this definition. Okay. Now, I'm not going to go through the theorem for its existence. You can do it. It's kind of similar to GCD. I'm going to give you another theorem. And actually, you can use this theorem to prove the existence of LCM as well. So this is the theorem. So let A and B be integers, not both of them 0. Not both 0. And yeah, for the previous one, I could also say not both 0. Right, can I say, so can I look at the least common multiple of, for example, 0 and 5? What is the least common multiple of 0 and 5? Doesn't really make much sense. So let's say be non-zero integers. Again, you can go back and extend the definitions for the case of 0. I don't really care about 0. Okay, because we cannot divide by 0 anyway. So let A and B be non-zero integers. I claim this. I claim that GCD of AB times LCM of AB is equal to A times B. Okay, why is this the case? Give me an argument for this.
without factorization.
Yes, without prime factorization. We're going to see prime factorization after this. We're actually going to use all of these theorems to prove prime factorization, so we don't have it right now. So here's what I'm going to do. Let's give this a name. Let's say GCD of A and B is D. Okay. What do I know about this D? I know that D divides A. I know that D divides B. I know that D can be written as AX plus BY. These are all the things that I know so far about the GCD of A and B. Okay. So now, let's say that I look at the number L, which is A times B divided by this GCD. Okay. This is an integer because A is a multiple of D. I can't divide by D. Right. I want to say that this L has all the properties of LCM. And if I show that, I've also shown that LCM exists, right? Okay. How can I do this? First, I want to show that A divides L and B divides L. How do you suggest I prove this? That A divides L and B divides
In another way.
divide what?
B is just the integer.
Which one of the previous theorems can I use? I had this theorem that if GCD of A and B is D, then the GCD of A over D and B over D is 1. Right? So maybe instead of using this one, I can also use this one. GCD of A over D and B over D is 1. Okay. Does this help? So this means that if I take A over D and B over D, there is some combination of them. That gives me 1. Does this help? I'm not going to solve this until you tell me how to solve.
Itself is just dividing D to the both sides.
Okay, but that's going to just help us with this, right? So here's what I can do. I can say that L is A times B over D, and B over D is an integer, right? So this means that A divides L, because L is A times something. And then similarly, I can say L is B times A over D. And again, this A over D is an integer. So L is a multiple of B. But so far, all I've proven is that L is a common multiple of A and B. Right? So I've proven this one. Oh, I forgot something, sorry. I need an absolute value right here because A times B can be negative. Right, so let's A and B be positive integers, let's say. Then for the negative ones, you just take absolute value. Okay. I want to say that for every L prime that is a common multiple of A and B, L divides L prime. Okay. So suppose L prime is a common multiple of A and B. Okay. So this means that A divides L prime and B also divides L prime. Why does L divide L prime?
That later on. Yeah.
No, well, we want to show, for us here, L is just A times B divided by B. We want to show that L satisfies the definition of LC. Try to get a contradiction. Try assuming that L does not divide L prime. And get a contradiction out of it. Or try to write L prime as some expression and then get L out of that expression. So show that L prime is L times something.
So for the equation that D prime, that so you put less than D, and D the so the conflicts other D prime less than
Not sure. Okay. Okay, yeah, well, kind of, yes. So here's what I want to do. I want to look at L prime over L. Right, and I want to show that this is an integer. Right. How can I do this? So what is L prime? It's A times B over D. So L prime over L is just A times B over D times L. Why is this? Sorry, no. L prime. L was, oops, I forgot that. So what do I want to say? I'm saying that L prime is a common multiple of A and B. I want to say that L prime is a multiple of L. So this is L prime, and L was A times B over D. So this is L prime times D over A times B. Right. So what do I know about D? I know that D is the GCD of A and B. So I should be able to write D as a linear combination of A and B. So this is going to be L prime times sum AX plus BY divided by A times B. I want to show that this thing is an integer. Let's just divide it into parts. Let's just extend this. I can write this as L prime AX over A times B plus L prime BY over A times B. Okay. On this side, I can cancel the A's. On this side, I can cancel the B's. Okay. But here's the thing. L prime was a multiple of B. Right? So L prime over B is an integer. So I can write this one as L prime over B times X. This is the multiplication of two integers. Right? And L prime was also a multiple of A. So I can write this one as L prime over A, which is an integer, times Y. So this is also a multiplication of two integers. So L prime over L is an integer. It's a weird integer, but it's an integer. Right? So L prime is a multiple of L. L divides L prime. And this shows that this condition is satisfied. So for every L prime that is a multiple of both A and B, L prime is also a multiple of that. So with one theorem, again, I proved two things. I proved that the lowest common multiple exists, and I proved that it's basically A times B divided by the GCD. Okay. So these are the techniques that we will use very often. It's like you want to show that some number divides some other number, just write it as a fraction, try to simplify it, try to get to a point where you say this fraction is equal to an integer. Right? Or just take L prime, try to expand it as some multiplication that has L as one part and something else as the other. Okay. Great. So now we have another definition for saying when two numbers are relatively prime, right? By the way, here in this thing, I said that A and B are positive. If they're not positive here, instead of A times B, you will just have the absolute value of A times B. Right? So that's the only thing that changes there. But here's another simple theorem. Let's maybe call it a corollary. I can say if A and B are positive numbers, then A and B are relatively prime if and only if their lowest common multiple is just their product. Because remember, they're relatively prime if and only if their GCD is 1, and if the GCD is 1, then the LCM has to be the product, because GCD times LCM is the product. Okay. Finally, we're going to get to the definition that we like, which is a prime number. We say that an integer p greater than 1 is prime if its only divisors are 1, p, and minus p. So very importantly, in our definition, 1 itself is not a prime number. So the smallest prime number is 2. And you can check that this matches the normal definition that you have of prime numbers. So 2, 3, 5, and so on are primes. And I'm only taking the positive integers as primes. Okay. Great. So here's another theorem, pretty easy. So from now on, I use P and Q and so on to show prime numbers. And I use like N, M, S, T, so on to show any number. So whenever I write P, I mean that it's a prime. Oh yes, minus 1 as well. I always forget this. Okay. So I want to say that if P is a prime, and P divides AB, then P divides A or P divides B. Again, our life would be so much easier if we just had prime factorization, but we're building towards prime factorization. We don't have it yet. Okay. So here's the thing. Let's just do a casework. I take my prime P and I say, well, there are two cases. Either P is a divisor of A, in which case I'm happy, or P is not a divisor of A. Okay, so that's the case that I have to solve. If P is a divisor of A, then the theorem holds. I don't have to prove anything. So suppose that P is not a divisor of A. Now, with this assumption, I have to show that P is a divisor of B. Okay, but what does it mean that P is not a divisor of A? what does it mean in terms of the GCD of P and A? So what is the GCD of P and A? Look, when I'm talking about GCD, I'm only looking at non-negative or basically positive divisors in this case. So I don't care about -1 and -p. The GCD of P and A cannot be P, because that would mean that P is a divisor of A. So the GCD of P and A has to be 1. Okay? But here's the thing. P divides AB, GCD of A and P is 1, so P should divide B. Remember, we had this lemma from before. Where is it? Euclid's lemma. If a number A, in this case P, divides the product of two other numbers and its GCD with one of them is 1, then it divides the other one. We proved this in the morning, right? So coming back here, P divides AB, GCD of P and A is 1. So by Euclid's lemma, P divides B. Okay, this is a great theorem because it says that whenever I have a prime number that is dividing a product, I can be sure that it divides one of the two sides of the product. And I'm going to use it for tons of other things. So I can just immediately get a corollary out of this. So this is my corollary. I want to say that if P divides some product of more than one number, more than two numbers. So I don't know, A1 times A2, so on to AN. Then P should divide one of the AIs. Then there exists some index I such that P divides AI. How can you prove this? Just apply induction to the previous theorem. Right? So I look at this sequence of products. I say I divide it into two parts. It's like either P divides A1 or P divides this part. Right? If P divides A1, I'm happy. Otherwise, P divides this part. I continue doing the same thing. I say either P divides A2 or it divides the rest of it. And I keep doing this. So there exists some I where P divides AI. Okay. Now, suppose that instead of just taking a product of arbitrary numbers, I take a product of primes. So remember, when I write P, I mean that this is a prime number. But when I write A something, I just mean that it's some integer. Okay. But here's another corollary. Suppose that I have this P and it divides a product of other prime numbers, Q1 times Q2 to Qn. And in this case, P is prime. And every Qi is also prime. Then there exists a particular I where P is actually exactly equal to Qi. Okay. And this is again kind of the same as the one before, right? So there should be a Qi where P divides Qi, and also the GCD of P and Qi would not be 1 because P divides Qi, right? But if P divides Qi and Qi is a prime, the only positive divisors of Qi are 1 and Qi. P is not 1 because P is prime, so P has to be Qi. Okay, so it's just this one with the extra addition that if P divides Qi, then P has to be equal to Q. Okay. Are you ready for this? We finally have the fundamental theorem of arithmetic. And then after this, you will not suffer anymore. So it says that if I have any natural number n, or any positive integer n, let's say greater than 1, because I also don't want to talk about 1, I can write it as a product of primes. And also this product is unique. So for every integer n greater than 1, we can write n equals p1, p2 to pk, where every pi is a prime. So I'm not saying that these are distinct primes. Some of the pi's might be the same prime. Okay, I'm just saying that I can take my number n and I can write it as a product of prime numbers, right? But I also want to say that this product is unique. But of course, it's not unique in the sense that if you look at the number 6, for example, it's 2 times 3, but I can also write it as 3 times 2, right? I can change the order. So I want to avoid changing the orders. So I say this, where every pi is a prime, and let's say I've sorted them. So p1 is less than or equal to p2, so on, less than or equal to pk. This is called a prime factorization of n. This is called actually the prime factorization of n. And it is unique. Okay. I needed this part in order to have uniqueness so that I cannot just reorder my prime numbers. I have to always write them from the smallest to the largest. Okay. So we have to prove 2 things. We have to prove existence. We have to prove that if I give you any number n, you can do this. And then we have to prove uniqueness. How do you prove existence? Yes. So let's go back to our definition of prime, and let me actually define a composite number here as well. So I say an integer n greater than 1 that is not prime is composite. Okay. So composite just means not prime, except that 1 is neither prime nor composite. 1 is just 1. Okay. So I'm going to prove this by an induction. I'm going to do a strong induction on my number n. Okay. So proof by strong induction on n. By the way, this is just for the existence. I just want to show that this kind of factorization exists. I say, let's do a strong induction on n. My base case is when n is 2. And you can verify that 2 is indeed equal to 2. So that's my base case. That's the prime factorization of 2. I can also do more base cases. You can do 3 and 4 and so on if you want, but 1 base case is enough. So 2 is equal to 2. Now, I say consider the number n, and suppose that every number smaller than n has a prime factorization. So that's my induction hypothesis, that any number smaller than n, well, between 2 and n, has a prime factorization. Again, 1 is a very special case, and we don't even talk about 0. So any number between 2 and n has a prime factorization. That's my induction hypothesis. Okay. So induction hypothesis says that for every m, if m is between 2 and n minus 1, then m has a prime factorization. Okay. So now I look at my number n. I say I have 2 cases. Either n is prime or n is composite. Case 1, if n is prime, then what? Well, n is equal to n, and this is a prime factorization. Case 2, if n is not prime, if n is composite, what does that really mean? So the definition of prime was that the only positive divisors of this number is itself and 1, right? So if it's not prime, it means that it has a positive divisor other than 1 and itself. So if n is composite, there exists some number a, some divisor a, that is bigger than 1 and smaller than n, such that a divides n. That's just definition of composites, right? So since a divides n, let's say that n is a times b. Okay. A is at least 2, and it's at most n, or at most n minus 1. So A has a prime factorization. B is at least 2, and it's at most n minus 1. So B has a prime factorization. Just put the two prime factorizations together, that's a prime factorization for A. Okay, so I'm going to have a prime factorization for A. Let's call it P1, P2, so on to Pk. And I'm going to have a prime factorization for B. Let's call this Q1, Q2 to Qt. Then I know that n is just the multiplication of this. So P1 to Pk times Q1 to Qt. Technically, this might not be a prime factorization because I said that my prime factorization should be sorted. So just sort these things. Okay, sort it, and then it gives you a prime factorization. Okay, so we've proven existence. We've proven that for every natural number n, there is a prime factorization of n. But now we want to prove uniqueness. So I know that I can write n as a product of prime numbers. What if I can write it in two different ways? So suppose I have two different factorizations. Suppose I have this. Let's say n is P1 times P2, so on to Pk. And these are all primes. But it's also equal to Q1 times Q2, so on to, let's call it Qs. I don't even know that these two factorizations will have the same number of primes, right? So I'm just assuming that I have two different factorizations, and I want to somehow get a contradiction out of this. Okay. So here's my claim. I claim that there exists some index I such that Qi is equal to P1. Why is that the case? Yeah, because P1 divides this, right? I literally have P1 here. So P1 should divide this side as well. But by this corollary here, if P1 divides a product of other prime numbers, then P1 is equal to one of those prime numbers, right? So there exists some I where Qi is equal to P1. So I just say cancel P1 and Qi from the two sides. Okay, so forget about this n part here. Just cancel P1 and find Qi wherever it is and cancel that. Okay. Now I can continue. Now I can do this with P2. I can say there is another index I where Qi is equal to P2. Right. Cancel those. So I cancel P2 and I find P2 somewhere else here. I cancel that. And I keep doing this. And I will never get stuck. Right? It will continue until I cancel everything on the left-hand side. But when I cancel everything on the left-hand side, my right-hand side has to be 1 as well, because my left-hand side has become 1 and the two sides were always equal. So this means that I basically found every prime on the left exactly once on the right, and I canceled them together. So the prime factorization on the right was the same as the prime factorization on the left. So I have only one prime factorization. Okay, this is the uniqueness. Great. So of course, this is not really how we write the prime factorizations, right? So if I have a number, for example, let's say, again, my favorite number, let's say 720. Or no, actually, my favorite number is this one, 444. Okay. What is the prime factorization of this number? Okay. So this is 2 times 2 times 3 times 7, right? But I would not write it like this. I would just write it as 2 to the power of 2 times 3 times 7. Okay?
No.
Ah, yeah, times 3 times 37, you're right. Yeah, I would write it like this. And of course, you can see that even with this representation, it's unique, right? Just sort it from the smallest prime to the largest prime, and you're merging primes that are the same. Okay. But now this gives us a different way of looking at numbers. So let's say that I have a number A that divides B. A has a prime factorization, and B also has a prime factorization. But if A divides B, that means the power of any prime in A's factorization is less than or equal to the power of this prime in B's factorization, right? And if I want to find the GCD of A and B, and let's say A is P1 to the power of alpha 1 times P2 to the power of alpha 2, so on to Pk to the power of alpha k. And let's say B is P1 to the power of beta 1, P2 to the power of beta 2, so on to Pk to the power of beta k. I'm using the same prime numbers here because if there is a prime number that appears in A but doesn't appear in B, I can just add it with the power of 0, right? So if I can write A like this and I can write B like this, what can I say about the GCD of A and B? This would just be P1 to the power of minimum of alpha 1 and beta 1, right? Times P2 to the power of minimum of alpha 2 and beta 2, and so on. Pk to the power of minimum of alpha k and beta k. So basically, for every prime number, I look at its power in A and I look at its power in B and I take the minimum. Now, if I want to do LCM, I just take the maximum. By the way, I'm saying all of these things. These are things that you should prove. But now that we have this theorem, proving all of these things is really easy. You should be able to easily prove this. So LCM of A and B is, again, this P1 to the power of maximum of alpha 1 and beta 1 times P2 to the power of maximum of alpha 2 and beta 2, so on to Pk to the power of maximum of alpha k and beta k. But then this really makes it easy to prove some of the previous theorems that we've seen. So for example, if I want to take GCD of AB times LCM of AB, what is that? That's going to be P1 to what power? To the power of minimum of alpha 1 beta 1 plus maximum of alpha 1 beta 1. But anyway, one of them is the minimum, one of them is the maximum. Minimum plus maximum is just the sum of the two numbers, right? And then times P2 to the power of minimum of alpha 2 and beta 2 plus maximum of alpha 2 and beta 2. Again, you have two numbers. You're adding the smaller one to the larger one. That's just summing the two numbers. So P2 to the power of alpha 2 plus beta 2, and so on to Pk to the power of alpha k plus beta k. But this is just A times B. So that's painful theorem that GCD times LCM is A times B suddenly becomes trivial. Okay. One more theorem. And this is a theorem that we have proven before, but we're going to prove it now using this fundamental theorem of arithmetic. Square root 2 is irrational. Okay. Why? So we say that suppose square root 2 is not irrational. So square root 2 is A over B, where A and B are positive integers. Okay. Then what? Then I can just raise both sides to the power of 2. So 2 is A squared over B squared. Okay. So 2B squared is equal to A squared. But what does this mean? So the left-hand side has a 2. And we have uniqueness of factorization. So if I factorize A squared, 2 appears as a prime number in that factorization. But if 2 appears in the prime factorization of A squared, it should also appear in the prime factorization of A itself. Right? But if 2 appears in the prime factorization of A, then 2 to the power of 2 or 4 should appear in the prime factorization of A squared, which means that 2 appears in the prime factorization of B squared, which gets us back to this idea that, well, both A and B are even. And well, I could just say, suppose that square root of 2 is A over B, and I could say that suppose this is an irreducible fraction, right? If I can write anything as a fraction, I can write it as an irreducible fraction, which means that the GCD of the two sides is 1. But now I proved that both A and B are even, so GCD of A and B is at least 2. This is a contradiction. It shows that square root of 2 is irrational. Okay, one more theorem. And again, this is something we've seen before. There are infinitely many primes. Okay. Suppose that there are only a finite number of primes. Suppose P1, P2 to Pn are all the prime numbers. All possible primes. Okay. Let Q be the product of all of this. So P1 times P2, so on to Pn plus 1. Okay. None of the Pi's is a divisor of Q. Because if Pi is a divisor of Q, since Pi is also a divisor of this part, P1 to Pn, this would mean that Pi is a divisor of 1, which is impossible. Right? So none of the Pi's is a divisor of Q. But we know that every number has a prime factorization. So Q has a prime factorization. But in that prime factorization, none of these primes appear. So that prime factorization has to have another prime number in it. So these are not all the primes. And that shows that there are infinitely many primes. Okay. One last point, and you can just use induction on the previous theorem to prove this. And this is next theorem. I want to say, suppose Pn is the nth prime number. So for example, P1 would be 2, P2 would be 3, and so on. Then I have this. I have that Pn is less than or equal to 2 to the power of 2 to the power of n minus 1. Okay. I'm just going to tell you how to prove this. I'm not going to actually give you the proof. You just do an induction and you say, suppose this holds for all the previous prime numbers. So it holds for P1, P2 to Pn minus 1. Now, what do I know about Pn? I know that Pn is less than or equal to the product of the previous primes plus 1. And that's enough to prove this. Just put it into the induction and you'll see.